Okay, let's get started. Before we start the talk, just a small thing. So for the passing around the mic exercise, it would be ideal if you make yourself known when you have a question and then wait until the mic comes to you, okay? Good, okay, so with that, our afternoon speaker is Luca Ciambelli, who will tell us about null surprises. Not physics, okay.
I tried to write the title before you finish the introduction, but okay, thank you very much. It's a great pleasure to be here on the other side. I was telling Dario yesterday, last time I was here was 8 years ago, and it was Lacey School, so I was a young student, and it was a wonderful time. I came twice for 2 autumns, and so it's great to be on the other side. I really appreciate the invitation. And I have prepared, as I've been instructed, a 30 minutes discussion, and there should be a 30 minutes session. So I, of course, have much more to say. Those of you that know me know that very well. I can talk for a long while, but I really try to prepare something a bit broad, trying to go through the interest of hopefully all of you. And then if you feel like you want to explore and open any of the doors that I go through, please let me know and we can, of course, it's made on purpose. So actually the title that I sent was Null Physics, What Did I Miss? And since some people asked, the reference was to a song. So I don't know if you've seen the musical Alexander Hamilton. In the musical Alexander Hamilton, Thomas Jefferson go back in 1789 from Paris, where he was working with Lafayette, to the US, and he's asking, what did I miss? And a lot of things happened in the meanwhile. And the reference is that I hope I can convey to you what happened in the last 4 or 5 years that I've been working on, and that has something to do about null physics. So the discussion is organized around 5 main themes. So let me just start with the themes. I did it as a star. So if I put null physics in the middle, there are 5 threads that I want to talk about. Of course, the tapestry of null physics is much more than these 5 threads, but those are the ones that I've been contributing to in recent years and that I want to talk about. So there is a side which is Carolian physics. There's a side which I loosely call quantum information / black holes. There is a side that I call causal diamonds. And then there are a couple of gravitational sides. Here I put flat holography. And here I put something more like, I would say CQG in the sense of canonical quantization of gravity on null physics. And so these are kind of the 5 themes I want to go through. And as I said, I'm happy to be interrupted at any time. And I will also, apologies before I start, since it's a chalkboard talk, I will not write down all the papers and names and archive numbers. Many of you in this room have contributed massively to this topic, so I want to acknowledge you before I start. And whenever you should be there, I think of you being there, although maybe I not say it. So please, of course, thank you for the amazing contribution. And in particular, the more concrete plan covering these 5 areas is that we start talking about geometry of null hyper surfaces and dynamics. So I will have in mind gravity, and I will have in mind induced Einstein equation of null hyper surfaces. I will then cover some of the phase space induced by gravity and this quantization. These are the recent couple of works. Connected to the themes of this workshop a bit more probably is point number 3, in which I will take everything I said in point 1 and 2 and try to see if there is a meaningful asymptotic limit towards Cry, and talk about my recent work with Tom Venstein and Laurent Beaulieu about extended BMS anomalies, which is a very interesting topic. Number 4, I will review for you the GSL. So sorry, I should say, stop me if acronyms are becoming too much, but when I do chalkboard, I have this tendency. I will review for you a bit of black hole physics, so the generalized second law, in particular the key elements in the proof by Aaron Wall in 2011, and the quantum focusing corrector. And although here I don't have anything very sharp to say, I think it's good to review those topics and keep in mind the possibility, which is the capability of generalize the generalized second law to any null hypersurfaces. This is a long discussion in the community, and I think we have some new elements that are interesting, although again, I will not have something more than an overview, if you want, of that physics. And the last thing is my recent works with work, singular for the moment, with Katrin Zurek and Temple He, in which we derive quantum area fluctuations, I hope I spell it right, from the covariant phase space by stretching a causal diamond. Okay, so these are the 5 topics, and again, I prepare something quite broad without too many details. Happy to go through if you want. Okay, so let me start with topic number 1. What I essentially would like to convey is that there is a, if you want, there was a concentration of people and ideas that led to a very nice and geometric reformulation of the conservation laws of gravity or of the Einstein equations once induced to a null hypersurface. This is a topic that goes back to probably Recciaduri and Damour, so at least 50 years ago, but Recciaduri even a bit more, Sachs in 62. So I'm trying just to give, if you want, a modern overview of that. And there has been an understanding of this in terms of Carolian language. Laura Donnet has a very important work with Charles Marteau in 2019, and many other followed and were precedent to them, ideas by Robert Penna as well. So there's a lot of physics there, but I want to start with geometry first to set up notation. So I will be very concrete. I have in mind a 4D manifold, a 3D null hypersurface that I'm gonna call calligraphic N, with 2D cuts that I'm gonna call calligraphic C. So that is my situation. And on N, on the null hypersurface of interest, I'm gonna set up what is rebranded into a Carolian structure. A Carolian structure, I'm gonna use generalized indices XA for the null hypersurface. So XA are 3D indices. You can think of them in practice, for instance, as U ZZ bar, excuse me, or V ZZ bar. And the Carolian structure is a nowhere vanishing vector field and the metric QAB, which is, however, degenerate. Okay, so this is, you should think of this as the same as giving a metric on a pseudo-Riemannian manifold. Okay, now by construction, you cannot lower the index of L in this trivial way, you would hit 0. And so there is a way to talk about projection by introducing the tangent bundle dual to L, so you can by hand introduce a conform dual to L, and given that you can introduce a projector to the base, which is just delta AB minus KA LB. This projects to the cuts. Now, maybe a very, very important point, and I especially recently with what is going on behind doors, I think I should insist on that. Not have a null hypersurface twist-free, finally parameterized that is inextensible in the middle of a manifold in gravity. This will develop caustics. Caustics are physical. Caustics are just focusing of rays. It follows quite simply actually from the Recciaduri equation that I'm gonna talk about. And so I'm gonna restrict myself to a portion of a null hypersurface that is between 2 caustics. The picture that you can have in mind is that it is something like this. So I'm drawing the geodesic generators, and there are tips that will develop at finite time at the end that I'm cutting off topologically. The only 2 well-defined caustic-free, inextensible null hypersurfaces are the black hole horizons of stationary black holes. This is called the teleological boundary condition, and asymptotic infinity. Any other, you will have to tip it, and it's a very important topic in the MathGR community to understand how we deal with caustics, okay? So there is nothing surprising on the fact that my Carolian structure will pertain to a middle of an null hypersurface between two caustics, because that's what happens every time you look at a lake, at the bottom of the lake, right? Caustics formation. Okay, now the very important quantity is the expansion tensor, which is 1/2 the Lie derivative along L of QAB. And I'm gonna raise and lower the indices with the help of this projector and define a mixed index expansion tensor that contains the expansion plus the trace-free object. That's why I want the mixed index guy. The trace-free object is called the shear. Now, if I do linearize gravity perturbatively and I choose the right set of conditions for my gauge for the metric perturbation, this object contains the two polarization of the perturbed graviton. Okay, so you could think of the shear, of course this is a gauge-dependent statement as I'm making it here, but you can think of the shear as containing gravitational radiation. We will see that from the phase space. Okay? Now, in all of this, there is a beautiful piece of literature that is actually surprisingly recent, in 2021, the Sakaran, Flanagan, Shehzad, and Speranza defined a null equivalent of the Brown-York tensor by defining the induced rigging connection on the null hypersurface. They define this object. Oops. And they've shown a beautiful equation which summarizes essentially this first part, that its conservation law. Oh, I have to establish a notation here. I will use a tensor with the index L down sometimes as the contraction of the tensor with L. And they defined this equation, and they show that this equation is nothing but bulk Einstein equations projecting on the hypersurface. So this is a very concrete and also very compact way to gather together many, many decades of works in this topic. It essentially readily encapsulate the fact that Einstein equations become conservation laws while projected. This is something that, as I was mentioning, has been done by many people at SCRI with Marius, during my PhD thesis. We were trying to write these equations. We were writing these equations, and on the horizon, as I said, Laura and Charles. So these essentially encapsulate the idea of the membrane paradigm in a more, if you want, refined and geometric version. Okay? Of course, there are open questions. And before them, let me write two equations that are maybe more familiar to some of you. First of all, you can contract this equation on its temporal part. And let me assume for the moment that there is no matter. And if I do that, if I contract it on the temporal part, I get an equation which is the Lie derivative plus theta of theta. It's equal to mu theta minus, minus theta squared minus sigma AB, sigma BA. Okay? And I apologize, the theta squared, I already put it on the left-hand side. Now, this equation, where mu, I'm not choosing an affine congruence necessarily. Mu contains the inaffinity parameter. This equation is the Ricciarduri equation. It's a null Ricciarduri equation. It's the temporal part of the Einstein equations. And if you projected it on the space orthogonal to L and Q, that's exactly what our projector is designed to do, QBC. This gives an analog equation for pi A that I haven't introduced and I will not unless required. That is the, what am I writing? dBQAB minus sigma B, which is the equation written by Damour in his master memoir, and then in his famous PhD thesis. Okay, so this is the Ricciarduri and Damour equations. They are the projection on this conservation law on the null hypersurface. On any null hypersurface, of course, Damour and Ricciarduri were interested in black holes, but this is true on any null hypersurface. Exactly. Let me point out that. Thank you. I was about to mention the Ricciarduri equation that is written there is Sachs. It's written by Sachs, but because Ricciarduri in '55 wrote the time like Ricciarduri. The time like Ricciarduri is exactly the same equation with a 3 down here instead of a 2, And Sachs wrote these equations in 62, and they are called Null Reciaduri, but they've been written by Sachs. Thank you. Of course, that's important. Okay, questions in these topics are things like, what are the properties of this stress tensor? Is it a fluid? A stress tensor is a stress tensor. These are conservation laws. Is it a fluid? So can we set up energy, pressure, heat, shear viscosity? Can we construct a derivative expansion? Fluids are perturbations around equilibrium. What is equilibrium? That's already a good question. What is a temperature? We don't have a notion of temperature here. As far as I know, there is not a universally understood and accepted notion of Carolean temperature for these kind of fluids. So there are many questions. Another question is this stress tensor useful for numerical GR on null hypersurfaces? So the characteristic problem is a lot by numerical GR people to simulate the formation of black holes. And so the question is, can I use this stress tensor as much as the Brown-York stress tensor used a lot in the 3+1 formulation of time-like numerical GR? And this is an undergoing investigation, and I think it's very interesting. It might be useful, it might be not. Okay, so let me move to point 2. I'm already a bit late. Let me talk a bit about the phase space. Now that I set up all of this, and if you notice, I try to be as intrinsic as possible. I actually never even introduce a bulk metric and an induced procedure. I have in mind an R-rigging induced procedure, but it doesn't matter for what I've been said so far. And so the whole point is that the stress tensor can be decomposed. It can be decomposed in a part that is along L and in a part that is orthogonal to L. These are momenta of the stress tensor. And if you do that, there is a symplectic potential that you can write down on the null hypersurface, which is, am I getting the 1/2 right? Yes, I am. Tau AB delta QAB minus tau A delta LA. And now this can be shown to be, derived from the Einstein symplectic potential once projected. The Einstein symplectic potential is a d-1,1 form. It can be projected on any d-1, so on any hypersurface. Projecting on n, you get this modulo delta exact and the exact terms that we can talk about and that are fascinating, but that I'm putting under the carpet. What is this? This is the null analog of what you would write on a time-like or space-like hypersurface. G mu nu is the geometric data, here L and Q, and T mu nu is the momenta, here tau AB and tau A.
So is this presymplectic potential coming from Einstein-Hilbert, or you have to add some boundary term to the action to get this canonical form?
It's Einstein-Hilbert with the d-exact term. So it's not exactly Einstein-Hilbert. There is a d-exact term.
Okay, thanks.
You have to deal with the angle at the corner. I can show you later. Yeah. Andrea, yes?
So to match soft terms to asymptotic symmetries using symplectic potential, it's important that one starts from a time-like hypersurface and then pushes it to the boundary because the normals are different, and that will result in a difference.
Yeah, I have something to say about that in point 3. Not a complete answer, probably, to that question, but I'll have something to say there.
Okay.
It's not a done thing yet. It's actually a pending, interesting question. Let's start with the null guy, push it to infinity. Can we define and understand what are the right corner terms that we have to make in order to recover? It's open. Ashtekar and Simone Speziale, and Abai Ashtekar and Simone Speziale have a paper last year where they comment about something, but it's not yet completely answered. I will be able to get only actually, in point 3, I can anticipate the bulk piece. So the Ashtekar-Strobel piece in the bulk. So the CAB delta and AB, but not the tips. Okay, so if you take this object, you know the drill, you can compute the charges, right? You take the symplectic to form, and then you contract the symplectic to form with the symplectomorphism, and then you can write out of this the charges. What you get is that essentially, since this is anomalous free, you can directly compute q psi equal I psi of theta can. And what you get, surprise, surprise, you get that if Anthony, Van, Anna, and Flans call it the null Brown-York, there is a reason. And the reason is this one. And the reason is that once you contract, let me get the signs right, you get exactly psi A, dB, TAB, plus this. Okay? Such that on shell you can verify Noether-second theorem. On shell, this object should become a corner data. I mean, I should strictly speaking say that this is the boundary of N, and that the charge is written here as a contraction. This object is the contracted guy that consider the one form normal to the cuts. Okay?
Sorry, is tau AB there the shear? Or?
Tau, yes, that's a good question. So tau AB is not only the shear. A piece is the shear, and then it has a second piece, which is mu times QAB. So I'm going to talk about that right now, actually. The right
so you're considering the kappa is a non-geodesic?
Non-geodesic yet. Yes, sorry, geodesic, but not finally parameterized. That's the inaffinity.
Your kappa is not the Newman-Penrose kappa then?
No.
Okay, your kappa is Newman-Penrose epsilon.
Is the inaffinity, which I think is epsilon, but
yeah,
it's the.
Sorry. Okay.
So let me give you the equation, maybe. The equation would be this. Wait, sorry, this. This defines my kappa. It's defined that way. That's epsilon. Yeah, I was almost sure, but I didn't want to say yes without being. And you should know, not me. Yes, exactly. So this is the inaffinity. So it's geodesic, but not finally parameterized. And you're touching on an important point. So what is tau? And that's the next step. The next step is that I still need to decompose. So this object is, for the moment, a 3x3 matrix. It's orthogonal to L and K, so it becomes a 2x2. But it has a shear trace-free part and a trace-full part. So it still contains a spin 2 and a spin 0 degrees of freedom. And that's what I'm going to do now. I'm going to take these quantities and split them into their spin decomposition. And the spin decomposition is trivial. It's just the number of A, B indices that you can attach to those. And there is an obvious spin 0 object, which is the area. The area comes from the fact that this degenerate metric has minors that can be that have a non-trivial determinant. So I'm going to take out the determinant of these minors and define a QAB like this. This is called also unimodular decomposition. It takes out the area of this object. And its partner is going to be this mu object that I said before. So there are going to be a symplectic partner of omega that is mu. That's the reason why I introduced this ad hoc sum of terms. The spin 1 data are going to be pi A and LA. And the spin 2 data are sigma B, which is symmetric, traceless, and orthogonal to L. So it's a 3x3 matrix, it becomes a 2x2, and it is traceless, so it's 2 degrees of freedom. And the partner must be therefore a 2 degrees of freedom tensor, and this is this object, because it was 3, but I took out the determinant. Okay, so spin 2, spin 1, spin 0. If you notice, and unfortunately those equations I think have been erased, the Recciaduri constraint had only, didn't have pi, and so I'm going to focus on Recciaduri, and I'm going to therefore throw out the spin 1. The Damour phase space is actually work in progress. I think we're going to be done soon, but it took me a couple of years, so I don't have anything to say at this stage. I want to finish it properly before making any big statement. So I'm going to focus on spin 0, spin 2. And the main idea is that this phase space, I have the brackets. I'm not going to write them down. They're very ugly. But I have the Poisson brackets, and I can see, is there a sense in which, a meaningful sense in which I can promote those two quantum operators? So can I use Dirac procedure on these brackets? And I will see that in a precise subsector of the theory, I can prove that the quantization scheme I will use makes sense. In general, it will remain a conjecture at this stage. I'm not able to do it in general. Otherwise, I would have done something quite remarkable, although in general there are, at least perturbatively, I actually have perturbatively now in the gravitons, I have some good results. So the main idea is the following. The Ricciarduri constraint, since I throw away the spin 1 degrees of freedom, I'm gonna go in a gauge where L is partial T. This is fixed on my phase space. The Ricciarduri constraint that I wrote before, that was the contraction, can be rewritten in this way. Let me get it right. This was theta, so it's dv omega. And then it's plus omega sigma square. So this is my Ricciarduri constraint. And now I'm gonna smear it, as usual, and define a current. So I'm gonna smear it with the current on F. And now I have that this guy does two things for me. The first thing that it does is that it generates symmetries. This shouldn't surprise anyone. We know that Einstein equations generate symmetries. In particular, I'm sorry, F here is the time component of a vector field, right? So the Ricciarduri is the time component of Einstein equation. So I'm gonna consider a vector field that has all the piece in time, and what it's doing is generating time reparametrization on the null hypersurface. That's what the Ricciarduri constraint does. And it does a second thing, which is it satisfies an algebra. That should also not be surprising at the classical level. Minus a pi g c fg. And the whole idea is that if you put these two things together, you can make a prediction, which is that the local object, if promoted to a quantum operator with this precise numerics, I will tell you why that precise numerics, I didn't impose it, I found it, satisfies an OPE limit, so when I bring x1 and x2 together, that has this form. And there is a delta of space. Yes, let me just maybe comment one thing, Roman, and then I'll take your question. So the first thing that I want to comment is for people that are not used to it. This is the OPE of, well, it's the chiral sector of the OPE of a 2D stress tensor in conformal field theory. And this comes about because there is a regime in the theory where I can prove that. And what I've used are two facts. I used the fact that is ultra-local. I didn't show that, but the Poisson brackets ultra-localize on the base. This is just a feature of null physics. The null cone of a null of the point on the sphere of a null hypersurface is a null line. It's not a cone. So neighborhood point don't talk. This is in this fact. And the second fact is that on null there's no intrinsic meaning of length. So I inheritedly achieve conformal transformation in the null time. So that is why we propose that, and this can be explicitly checked, and I can compute the value of the central charge explicitly for some simple subsystem of this complicated gravitational system. It's a CFT of geometric data. There are no, I'm not adding matter here. This is really the geometry itself, the area, the inaffinity, spin 2. Roman.
So the canonical generator that you're writing, they're related to the charges that you wrote before? Coming from the symplectic structure? Or?
Absolutely. So I'm throwing away corners. So I'm literally quantizing the kinetic space. I have something to say about that in a moment, but absolutely. So if you take qxi was ixi theta, and this object is integral over n of, sorry, cf plus a corner term. So I'm quantizing the constraints directly. And I'm also throwing away corner terms. So this is not the algebra of Noether charges. This is the algebra of fluxes, if you want to read it that way. It's the algebra of gravitational constraints directly.
And so here you are using the standard bracket. There is no modified bracket or anything related to the flux?
Oh, yeah, there's the standard bracket. Okay. Yeah, there's no modification. Also, notice that there is no modification because I'm restricting myself to a subsector of the theory where everything works. These charges will not be integral if I add corners, and I throw them away by hand. That's the topology tipping.
Sorry, I was just, and C is just the Einstein, the null components of the Einstein tensor.
Absolutely. That is what it is.
Sorry, what again fixes the value of the central charge C? It's a dimensionless number, right?
So very good. Thank you. This is dimensionless number. So first of all, the 1/2 here is Jalomoshnikov. I cannot put any other number here. This 1/2 makes this a 4. That's a fact. And the fact that it's dimensionless, you can see, is the reason why I put an L Planck square down here. It's GH bar down here. This object is dimensionless, but it's not a ratio of dimensionful quantities. It's a number. I'm going to talk about that in a moment. It's just a number.
But
No scales.
For pure Einstein gravity, for instance, you get just some
Yeah.
dimensionless number that you calculate. Okay, and what's the value of that number?
Okay, so let me give you the simplest possible answer. Suppose I do a system which is non-radiating, so I throw away by hand the spin 2. I literally have two fields, omega and mu, and their brackets actually they are an Heisenberg pair. So it's a delta function. Omega 1, that's the reason why I call omega a field. Omega 1, mu 1 omega 2 is delta 1, 2. I go in and I check the value of this number, and that number is 2. Then I'm not sure about that, and I tell myself, oh, maybe it's an accident. I have two fields, it gives me 2. Smells good, but let me re-add this thing perturbatively. So I add a complex scalar. A complex scalar perturbatively is a graviton, and then I get 4. The two scalars. So this is literally seems that is counting. Now these 2 and 4s were through per null ray. Now the per null ray, meaning that now I fix myself at x1 equal x2 equal on the base. But it's summed over null rays. And if you are familiar with the, well, sorry, not if, I know you are. You are familiar with the contraction that brings you down here. You know that the central charge comes from a double contraction. So this object is my C, right? And I throw away the spin 2. So it comes from this double contraction. Now each of them carries a delta function on the base. So I get a non-integrable distribution because I get delta 2 times delta 2. What is happening, I mean, you can see it very trivially if you put a UV regulator on the number of points. What is happening that this is counting the number of fields on each null ray times the number of null rays. And there is a comment about a free scalar field in Aaron wallpaper in 2011 about that, for a free scalar field. Here I'm getting it from gravity directly because the system effectively looks like a scalar field on a null hypersurface. So it's the number of fields on null ray per numbers of null ray. And strictly speaking, in gravity, classical gravity, the number is infinite because there are infinitely null rays departing from a sphere. It's a continuous, right? And this is actually a thing that leads to the next concept, which is, super late. I lied when I say I was doing half an hour, Andrea, I'm so sorry. to the next concept, which, I mean, maybe I go fast on that. That's more toward the quantum gravity community. We can talk about it more if you're interested. Is essentially the topic of how can you reconcile classical general covariance with the fact that in the quantization I'm using, I have a preferred notion of time, which we often do when we quantize. When we quantize, time is an external parameter of the theory, right? It's fixed. And how do I recombine that? By the fact that I have the central charge. So the classical theory is time reparametrization covariant. The central charge was 0. This was an algebra. If I compute the quantum algebra, of course I get the Schwarzschild. This is just a classical now chiral setter of a 2D CFT. So we know what is the commutator, the C prime of F prime transformed with the Schwarzschild. And so kind of an interesting feature toward the quantum gravity community is that a way to reconcile the appearance of a preferred quantum time with the general covariant classical theory is via an anomaly. That's what we are seeing. Time reparametrization is classical asymmetry, and quantum Lie, although quantum Lie is not an English word, but I like it, is an anomaly. Okay, if you want, we can talk about it later. It concludes this more or less the first 2 parts, so I'm happy to take some questions before I go asymptotic.
Yeah, just now I'm a bit confused about the charges that you are considering because they are 0 on shell, right?
Yes, they are 0 on shell, and I found the central charge. I should have perhaps insist on that a bit more.
Because usually the way that we define a large J transformation is by looking at non-vanishing charges. So I would say that the corner term is actually the one which is important.
No.
In the usual.
I agree with what you're saying 100%. So here what I'm doing is something much more before that. So this is the quantization directly of the Einstein constraint that you want to set to 0. The fact why at the end I backtrack and I say, oh, I did something useful and meaningful, is because I found this object. You know that if the central charge is not 0, I mean, this is just, again, standard 2D CFTs, but let me rephrase it for this theory, you cannot impose the classical constraint that generate that symmetry. If you define a state, you have C the constraint acting on the state being 0, that's an issue, right? Because if you add with the second one, by virtue of the algebra, you get little c acting on 0 being 0, and the only solution is little c equal to 0. So indeed, if the classical symmetry generator is anomalous free, you can impose it classically, and you can do reduced phase space quantization. If the classical symmetry generator at the quantum level is anomalous, you cannot impose the classical symmetry. And this is an a posteriori realization because a posteriori at the quantum level we found the central charge. And there's an interesting question. I mean, this quantization was naive, if you want, right? You can quantize the theory maybe in a more proper way by doing deformation quantization, and maybe something more interesting appears and the central charge can be cancelled by some mechanism. And then maybe you can impose the classical one. But I agree with you. I mean, at the end of the day, I want to set this guy to 0, and these are my observables at the corner. And those guys, I want to put a hat on them. But if this is already anomalous, I have to stop even before. That's kind of the logic.
What's the value of C? What is C?
Little c?
Yeah, what's its value?
It's the number of fields on null ray per number of null rays.
Oh, it depends on the matter. It depends on the matter.
Well, in this case, it's the number of geometric fields, and there's no matter here.
Oh, I see, so there's 2.
If you have only spin 0, correct.
Oh, I see, it's infinity.
Well, 2 times infinity, or 4 times infinity if you add the perturbative graviton. With the non-perturbative gravitons, I wasn't able to do it because the canonical quantization I'm doing will not be true. I'm trying to study some, Fedosov, Kontsevich, fancy things, but I'm learning them as I go through and try to see if it makes sense to do a more serious quantization that will capture these effects, but
just to check I'm understanding it right, the V is the coordinate up and down the null ray, and the delta function hiding in the corner, that's in the sphere.
yes.
So why are you getting something that looks like a Virasoro algebra in one real dimension? As you say, it's a 2D CFT thing.
Oh, where is the second one? I cannot see it. I would love to. I would love that to be on you. Well, maybe let me be precise. This is not. Sorry, not precise, but let me be clear. This is not on space, right? This is on time. So you have one here. It's like when you do Brown and no charges analysis in 3D, in ADS3. You have CFT2 on the boundary, and you have a light X plus and X minus. And here, essentially, one of the two I've cancelled it because it's the other direction, the point out of the null hypersurface. I'm reducing my phase space by taking this and projecting myself only here. There is probably a second one. It's a good open question to try to see the second one. I know Mark Klinger and Rob Lee have some work coming up, but the other one should be there. Actually, I don't even know if the other one should be there or if the other one should be there to compensate this and make the center charge 0. That's still an open question. This is the quantization not of gravity, of a very precise subsector of the Einstein equations. It's 1 out of the 10 that I had in the bulk. But if you ask it's the chiral of what, the other chiral direction would naturally be the other null direction. But I'm not be able to show that to you. It would be. So this would pertain to any dimensions. So the fact that there is a chiral sector or that there is a 2D CFT structure with the base, it would be true in any D, which is very different from having it on the base. That would depend on the dimensionality. Okay, so maybe I'll maybe I'll say really less technically. I feel like I am using my time not so wisely, but maybe let me say what is going on when I go to the asymptotic limit. The question, of course, is very natural right now, right? I have this quantization, I call it V, but I could have called it U, and I have scry plus, say, sitting here, and I have my big banana here. And the question is, what happens if I send these guys to infinity, right? To do that, I need to use a family of null hypersurfaces. This is not typically what we do in Bondi gauge. In bonding gauge, we fix the bonding gauge radial direction is a time-like stretch hypersurface like this. And so I still decided to use bonding gauge to do this analysis because I think I can connect better with the community. I could have done a more natural gauge to do that. You can do it in any gauge. And the motivation for doing this on top of curiosity was that it looks very similar to something we do in ADS, which is we foliate the bulk with hypersurfaces of the same geometric nature of the boundary. And by inducing our Brown-Yacht stress tensor there, we understand a lot of things about holographic renormalization, the interpolating dictionary. And so the one thing that I was curious about is that does it make sense to do this and what it gives. And of course, the first thing that you realize is that you have to map equations into equations. The first result is that the Ricciarduri equation C in the limit R to infinity becomes the bonding mass loss formula. This is a proof of concept. You have Einstein equation on a null hypersurface. You push it to infinity. You know that the Einstein equation on the null hypersurface, which is Cry, is the bonding mass loss formula. You must obtain that. The way you set up the foliation and the way you obtain that is actually geometrically interesting. The way you set up the null rigging procedure to induce things is interesting, but this is a proof of concept. The second, which is less of a proof of concept, and it's related to what Andrea was asking, is can we take the canonical symplectic potential that I have there and push it to infinity? And you can. And the first thing that you find, which is non-trivial at all, is that it is completely finite, no divergences, and it gives you the, I will definitely screw up this, but Andy will remember it for me, a 16 or 32, the Hachtecker-Strobel symplectic potential. Okay, of course, when I push it is Scry with the fact that I have to be careful that, as I said, I have to consider a finite portion in the bulk because of caustics, right? So it's Scry U minus U plus. Okay? And the third final thing is, well, okay, now I have also a new stress tensor that I can take the limit of. And this is very much under debate, the fate of this object, in the sense that I've written it. At leading order is satisfied restlessness condition. I can show that the Einstein equation in the boundary are conservation laws for the bonding mass loss formula explicitly, analytically. So this is the bonding mass loss formula, it's what I wrote before. And for the angular momentum, I have it only coded up in Mathematica. I wasn't able to write a nice expression for the limit, it's kind of ugly. But in the limit R to infinity of this object, I have a new stress tensor that sits there. It's not the most natural object. The mass and the shear appears at different orders in this parameter expansion. And I think it's an interesting challenge because this is what we use in SFT to define the one-point function of the boundary dual stress tensor. If I were to mimic exactly the SFT, I would put an expectation value in a state of the boundary of this object, and I would claim that that is the natural object. I look at it, and it doesn't look that natural for the moment, but I think it's worth investigating. Please.
I guess same question as to Marika last week, I guess. So this will not capture long-range interactions, right? Because you're cutting off at some fixed, finite U at the boundary.
Fundamentally, yes to that answer. There is a way that I'm trying to set up the problem in order to see if as I go to infinity, I'm able to do this. I can tell you later.
Okay, and second question, so for superrotations and so on, there's also usually large R divergences. Are you saying here that with your procedure you will, already have it renormalized?
Sorry, I don't know which one you're asking.
When you compute the symplectic structure.
Yeah, so for the moment, I haven't checked the corner contributions. So as you see, I have the integral here, and I haven't checked the corner contributions. The corner contribution might still be divergent in what I'm doing.
I'm just talking about large R divergences now?
Yeah, so I'm saying that I take this object, and for the moment, I'm tipping these guys off, and I'm computing it here. And here, there are no divergences, and you can take the full time reparameterization symmetry group is not divergent.
So this is cupping off U divergences in time, right? I'm just talking about R divergences.
Yeah, there are no R divergences in this object. I have to say, maybe that's important. I am on the physical space-time. It's a good question to do it on the conformally compactified one. And things change. The orders in R changes on the conformally compactified one. And we can talk about that later, but it's actually a hope for me to go conformally compactified even to retrieve the angular momentum equation. It seems to become more over the conformally compactified one, which is maybe related to what you're saying, that super rotations are become more overleading maybe than what I see here. But that's important. It's an open question.
Yeah, so if you allow some fluctuation of the transverse metric at finite distance, I would have expected to find some term proportional to that in the symplectic structure at null infinity. So for example, if you turn on superrotation, you get some variation of the boundary metric.
So this was to retrieve only the Astrakhan-Strobel without delta Q. Delta Q, AB, is completely zero in that computation. If you turn it on, the leading order of that guy couples to the delta R, and you get also the possibility to rescale. So this is related to the same question of Andrea. Here I was really focusing on time reparameterization, but if you want to add the angle, you will get the extra term that is already in the Astrakhan-Strobel paper in 82, by the way. It's exactly that term, and you find it here as well.
Then there is no divergence, because the divergences are proportional to
the only thing that I wanted to point out is that this is a divergence as you go all the way, but there might be a symplectic potential corner contribution here that is still R divergent. I haven't even studied those yet. That was what I was trying to say to you. But how is it going, Andrea? Am I behaving or not? Okay, so maybe I'll start with point 4. Let's see how far I get. And I want to say also something about point 5. Oh no, first I want to talk about EBMS anomalies very fast, because I think this is related to more to this community. And so the other thing that we did recently, so this was in my solo paper in January, but I have a paper with Tom and Laurent Beaulieu for a couple of months ago. The thing that we did recently was also to do BRST about on the extended BMS. So now I'm considering a completely changing page. I'm considering an intrinsic boundary theory. There is not even a bulk. I don't want to know that there is a bulk. And I'm going to put, this is a field theory, so there's no propagating gravity, and I'm going to require that it has extended BMS symmetry. And the extended BMS symmetry, to be precise, is the one that has super translation and the 2 super rotations. Okay? So now I have the symmetry, and I'm going to define my null structure to be very simple. So I take the 2 sphere, I take time to be partial U, and I take my Ehresmann, or if you want, dual one form to be the U. The thing that you get from the bulk, this is an input on the theory, is that the asymptotic shear appears in a very precise geometric place, which is in the connection. Okay, this I will not show it to you, although it's not hard to show. The connection that I'm working with is Ashtekar connection. So it parallel transport Q and L, but it does not parallel transport K. And it doesn't exactly because of the asymptotic shear. So this is an input. Of course, CAB is not a function of QAB, L, or K. So I'm working with the non-Levi-Civita connection. Ashtekar in 82 understood that the asymptotic shear is in the conformal class of boundary connections. And this is explicitly realized by the fact that this object is actually ambiguous. I didn't talk about that. And this is a concrete realization of that fact. Okay, you can show it by hand starting from the bulk, or you can posit that that's the place where it should happen in the boundary and take that as an input for your theory. Okay, let's see how far we get with that, and we get to the right place. If you go into the frame bundle, now I'm going to introduce a Carolian frame bundle. The spin connection contains CAB here. And if I now BRST, I introduce my BRST operator. This acts on the frame bundle. And my BRST gauge fixing tells you that the ghost that I introduce, everything here is going a bit fast, but eventually the BRST gauge fixing that preserves this, and that reduces to this diffeomorphism, which shouldn't be surprised, is exactly, so this is derived, is exactly the extended BMS. derived by the, Z bar. Okay, and in particular, you know that if you introduce in the first order, in the frame bundle, if you introduce the you do the BRST by grading, so you have d hat is equal to d plus s, where s is your BRST operator, the horizontality conditions, the fact that all the curvatures must be horizontal, which is also called the Darboux-Cartan-Ereshman-Morier equation, tells you, oh, thank you, I have a lot of time. Sorry, I didn't see you before. Tells you how your objects transform under the BRST. Right? So if you do it for a very simple gauge theory, you get the transformation of the Faddeev-Popov cost. You get SC equal 1/2 CC, and you get SA equal DC, right? They comes from this condition. And here you find the same. You find how all your geometric objects transform under BRST. And in particular, what you find is that S of C is ZZ bar. Let me be clear, there was no bulk here. Everything was done in the boundary. S is the boundary BRST operator. This is a field theory. There's no gravity. All of this is multiplied C ZZ bar. Okay? And now, this should sound familiar. This is what you find from the bulk when you do the asymptotic analysis. So it's an intrinsic boundary derivation. I like this a lot personally because we don't have a lot of, contrary to a DSFT, flat space holography has been massively derived from bulk to boundary, whereas in a DSFT we have a lot also of boundary to bulk, and this is a boundary computation. So I like this. I think it corresponds to something that a lot of people have done from the bulk, and so it's a purely boundary derivation. Once I have this beautiful nilpotent operator, I can classify anomalies. It's a theorem by Dubois-Violette, Marquenot, Talon, and Vialet. The fact that all the anomalies of this algebra can be written as wedge cocycles. And so I can literally sit down and write down the most general goes to weight 1, degree 3, because I'm on the boundary, space-time form degree 3, trace on the group of all possible contractions, and this classify automatically the anomaly structure of the theory. The generic structure that I get is that there is potentially an anomaly. There is potentially an anomaly. Oh, let me call them cocycles for the moment. A cocycle in super translations, in super rotation 1 and in super rotation 2, and a priori they are independent. This start to look very similar to what Henningson and Skanderis did in a DSFT in 1998, where they compute independently anomalies from the bulk toward the boundary and in the boundary. And they found a matching and they found an induced value of the central charge. I'm trying to do the same thing from the boundary. The first result that you find is that super translations are not anomalous and they don't have a cocycle. This has a bulk counterpart, which is very well known, which is the fact that the leading soft Weinberg soft theorem is 3-exact. And this is this fact from the boundary theory. Now I can see a boundary counterpart of that fact. And the second one is that 6i is different than 0 and 6i bar are different than 0. So super rotations can be anomalous, and the cocycle is exactly given by 1/2 dz wedge dz bar, wedge du partial u, computed from the boundary. Now I didn't tell you what kind of cohomology condition I was solving. Of course, that I put it under the carpet, but we can talk about it later if this is something you like. And this quantity has a beautiful bulk counterpart. When you prescribe the good fall-offs of shear, or you derive them, better even, this is the, in the bulk, is the one-loop infrared normalized log term. Okay? And this has been found by many people in the audience and by in the log omega piece by Ashok Sen and Sao from an independent computation, from the phase space Andrea. There's a lot of papers on this topic. Yes, there's a question. And so while the mic goes on, David, I just say something more 1 second. So this is again a intrinsic boundary analysis. Now there is a question that remains: is this where this appears? And the preliminary analysis indicates that it could appear in the mix of the holomorphic, anti-holomorphic currents in the base, but I can talk about that later.
So I can view these diffeomorphisms on the boundary as the bulk diffeomorphism.
Well, if you will connect it from the bulk, yes.
And in a theory of pure gravity in 4 dimensions, there are no diffeomorphism anomalies in the bulk.
Yeah, but it's very important. There's I put it under the carpet. Apologies. This is not an anomaly as much as it's a diffeomorphism anomaly from the bulk, because the cohomology I'm solving is not the DS exact cohomology. I can talk about it later a bit. There's a technical point there, but the technical point makes it a codimension 2. What you should retain from what I just said, and I can explain you later if you want, is this fact. Is the fact that it's a total boundary term. So in the usual standard BRST cohomology, the term will just be exact and you throw it away. But since a scry can have boundaries, you want to keep the term.
Is there some computation I could do in the bulk that would be sensitive to this? Or?
The dual bulk computation would be to go through the, Weinberg-Soft theorem corrections at one loop, etc. How to see that those are related is a paper of Tom Weinstein and Laurent Beaulieu prior to this work, which we can talk about later. It's about what they call the BRST 1.5 theorem. Sorry, the Noether 1.5 theorem, which is something we can talk about later. But there is a way to see that these two things match.
This is also just for the soft charge, no?
Yeah, this is the soft piece. So absolutely, thank you. If I didn't say it, that was important. Yes. Yeah, we can talk a bit later. Okay, so I have 5 minutes. I have 5 minutes. I think we can do a poll here, because in 5 minutes we want 4 or 5 by show hands. Who wants to hear about GSL and QFC? No one. Okay, some hands. You're not allowed to know what they are. You have to blind vote. No, GSL, generalized second law and quantum focusing conjectures on black hole horizon and on a generic null hypersurface. Are you voting for it or not? Because your vote now is crucial. Who wants to hear about quantum area fluctuations? I think there are more people. None. None of them. No, okay. I mean, I think I think there were more hands for the quantum area, so I'm going to talk briefly about that. And if you have questions about point 4, happy to talk about it later. So, to some extent, Marius, this fit more in 5 minutes than the other. So maybe I was lucky. So, okay, so what is this is about a recent paper that we put out with Temple and Katrin Zurek. Some of you heard it already because Temple gave a Celestial Saloon, so apologies for those that already heard it. Essentially, this goes back to an observation that Eric Verlinde and Katrin Zurek did in 2019, that if you take an interferometer with the beam splitter and an end mirror like this, and you draw his Penrose diagram, it looks like there is an array going out, bouncing off the mirror, coming back in, right? This can be done in a tabletop experiment, and the length of the arm, if the length of the arm is called L, if you assume a Planckian white noise, and you do power spectral analysis, you find that the length of the arm has a fluctuation that goes like LP times L. Now I'm going to do everything in 4D. So this is physical bulk. So LP is LP square is G Newton H bar. I'll call it G only. And so this result was just an observation that if you have Planckian white noise with a specific profile and you compute the power spectral decomposition, you get something like this. Why it's an interesting observation is because if you start putting numbers, this is 10 to the minus 18. And also is that if you do something very naive, and you say, how should this, allow me to call it IR scale, because it's the length of the interferometer, goes, you would naively say it goes like L itself, LP, LP itself, which is 10 to the minus 35, so it's much smaller. Okay, so this gives this so-called accumulation effect, and they propose that to be something that maybe can be seen, and the question is, can this effect be derived? The first observation of this effect is that if by some reason, which we can talk about, you want it to relate to a modular Hamiltonian, and your modular Hamiltonian in your theory is A over 4GH bar, with good reason to say that there are systems that do that. If there are systems that do that, and A goes like, of course, goes like L squaring for D, you immediately get that delta K square is bigger or equal than K. And this is something, the fluctuation of the modular Hamiltonians being determined by the modular Hamiltonian that can be derived in some theories like ADS-CFT. So it's a very interesting connection between a priori related topics. And so the question that we had is, okay, this is all very beautiful, but it comes from saying, oh, I have some noise that has a precise profile. Can I derive this effect? And so the effect, this effect can be derived for the moment only in very restrictive conditions. And the way to do it is that, unfortunately, studying this phase space, so it's a null hypersurface, a mirror, and the second null hypersurface is singular for many reasons, because we actually don't know how to, modelize the mirror itself. But on the other hand, going back to many decades ago, people have told us that we can do some stretching, right? So we can do some stretching and we can take a membrane like this, which is now a timeless surface on which my symplectic structure and the Einstein gravity, everything is well defined and pulls back regularly. Okay? And so essentially what we did with Catherine and Temple was to induce gravity on this null hypersurface, of this time-like hypersurface, solve now the Ricciarduri equation. This is a very subtle question, because if it is truly anomalous, what we did is a bit sketchy, but we were time-like yet. And then take the limit where this goes to 0. And so essentially project our phase space on the null. So this phase space was just spin 0 data. The spin 0 data were just the area in the normal direction, and what we found is the Poisson bracket that the area at point tau, so tau is the time-like time, and the normal derivative of tau evaluated at tau prime, we found that this, from the classical phase space on shell of the Ricciarduri constraint, is 4 pi g over h naught times the heaviside function, tau prime, tau minus tau prime, times del tau of omega tau. And essentially from here, you can use the Robinson uncertainty and derive that the time integrated quantities, so the integral from tau minus to tau plus of this area, so it's a cumulative effect, satisfies a commutator which is just this. Sorry, T is the total time duration. So I'm taking a time average of this effect times omega s itself. And from here, if you do Robinson uncertainty and you evaluate this, because this for the moment is true on any spherical symmetric configuration, but if you evaluated it on Minkowski, you know the value of omega s and the rho omega s in the coordinate system I'm using, you put them in, and
usually we do canonical quantization on space-like surfaces, so what are you trying to do here?
Fantastic. I was sure someone would ask that question. That's fantastic. Give me 1 second. I'll finish and answer. This is the most pending discussion. So thank you. Thank you. Okay, so what you get is from Robinson. Once you have the quantum commutator, you can take Robinson uncertainty. And Robinson uncertainty tells you that the variance has a bound. And the bound is that First of all, is finite in h naught goes to 0. And second of all is, well, I did it in NED, so there's this, the space-time, sorry, the dimension of the cut, but this is this. Because A goes like L square, and so you integrate, you take 2 square roots, and you get exactly this behavior. Now, back to your question. The answer is only partial, in the sense that we cannot really trust what we're doing on the time-like guy, but we can trust its leading order h naught limit, because if you take null, admittedly for an inextensible curve, Frolov have shown that it makes sense to canonically quantize there, and that the canonical quantization there is isomorphic to the space-like one. So in the leading h naught 0 I can trust, admittedly not even for what I'm doing, but for an inextensible one, and this is not inextensible, I put a mirror by hand, but that's what I can trust. I can trust the leading h, sorry, I should have, h naught is when this object comes here. That's h naught c, sorry, I should have insisted on that. Now what I do here, when h naught is finite, I shouldn't be trusted it. But since my effect that I wanted to reproduce was the null one, for the sake of what I'm doing at the end is fine, but it's a big question to go back and trying to understand. They are not unitarily equivalent. The time-like one doing on the stretch and the space-like, even if you take a free scalar field, I was talking with Prahar, he has some computation that they're not in a unitarily equivalent. And so, for the moment, it seems really that I shouldn't trust it at any finite value of h naught. So, thank you. That is a good question.
I don't even know what you would mean by evolution, but yeah.
Yeah, for sure, for sure. Okay, so this was the last thing I should point out, and I should really finish probably. So I just point out that we are doing the sitter, and it's telling us some cosmological scaling, which I think is super amusing, and that I should probably finish because Andrea is looking at me very badly. Thank you very much. Thanks.
Questions?
If you forget about gravity, you just have, I don't know, a refraction index that fluctuates on that system with a mirror and do you also get the fluctuation that goes like square root of the length of the arm?
So everything depends. So if you just do a quantum computation, it. Oh, yeah, you do something like that. Yeah, you can get it from random walks analysis.
So that's just random walks.
Yeah. Yeah, so this is the fact that if you take delta, delta n goes like square root of n when you compute the steps in a random walk. It's exactly the same scaling behavior. Actually, that is the reason why Verlinde and Zurek, after they wrote this in their first paper, they connected it with this, because they had in mind the random walks. So I think it's confusing to say, and I've said it in a couple of seminars and I regretted it, that this is an IR-UV mixing effect. I was saying that because on the right side you get a product of two scales. One that is UV and one that is IR. But I think it's, it resonates poorly in the mind of an effective field theorist, if I say something like that. So it's just a random walk statistic.
So the question I had, so with LIGO, if you compute the delta L over L, and that's LIGO is 4 kilometers and L is a light length, that's 10 minus 20. So that's LIGO measuring that kind of strain noise sensitivities.
Wrong frequency. I can show you later. Yeah, so I can explain it later a bit more in details. I have to say that I'm not completely on top of that answer, but I can point out where this is explained to you. Maybe you can explain it to me later. But I've asked those questions to the right people, and the answer was wrong frequency.
Any more questions? We already had a lot, but now is the time.
You got the log omega term. The 1 over omega must be more trivial
The 1 over omega in what I was doing was this fact, right? Was the fact that the super translation one does not get one loop corrected.
And omega log omega square, do you get it?
Not subleading. I don't know how to see it. Probably with what a lot of people in this room are discussing and doing with W1 plus infinity and with higher spin charges, there's a way to see that. It's a good question to do boundary classification of anomalies for a higher spin or a W1 plus infinity field theory. I don't know how to do that. Probably then one could say something about those. But I definitely don't see it here because it would be in the next leading or in the next order in the symmetries. Okay. Yeah, so I can stop only there. But no, I don't know.
So you need to compute your Lie algebra cohomology of the loop algebra of W1 plus infinity. I'm sure Kasia would have some comments. Oh, she's not here. Yeah.
Kasia is not here, probably.
Well, she has tried that kind of thing, but yeah. Some well-posed problem.
I feel like, people have almost everything to say it. I think probably they just never phrase it in these terms. Because I think in W1 plus infinity, there's more that has been done from this perspective. I don't know how to put it on the frame bundle, but we can talk about it later. Maybe you know. It was a technical step of what I did for computing the BRST action.
So I didn't quite understand what you meant by when you have a boundary computation. Do you have a boundary theory that whose fields are these psis somehow?
What was the verb? Sorry, that?
You said that the BRST charge S was some charge in some boundary theory. So do you have an actual boundary theory?
Yeah. Something I didn't say because of time. It's as much as you can classify anomalies. So this is you can study anomalies of a conformal field theory without knowing the field content of the theory.
So
right?
this is an anomaly inflow type argument.
This is Bonora computation in 1980. No, you can just do BRST classification. Or if you want, you can study, anyway. So you can do that, and that will give you just the anomaly structure of the theory. Now, whether you have a field theory that is sensitive to that, it depends by the background and a lot of information. But you can also do Lagrangians. And I have Lagrangians. So I have boundary field theoretical Lagrangians here that make sense from the cohomological analysis. These are just the 0 top degree forms analysis. The only thing is that the only Lagrangians I get are wedge products of Lagrangians. And there's not the beautiful theorem that Mark and friends did for anomalies. That is not the whole Lagrangian structure of the boundary. The most general Lagrangian this is true even in electromagnetism, is not always a wedge product. So I can compute all Lagrangians of the extended BMS field theory that can be written as a wedge product is already on the paper. But I cannot conclude that that's the most general structure, but yes.
Okay, I think we're going to close the discussion now. Thanks again to Luca.